Welcome back to an intuitive introduction to probability theory. Today, in the third lecture on conditional probabilities, I want to tell you about the multiplication rules in probability. When can we multiply probabilities, and what does that mean, and where do we have to be careful? So, the conditional probability definition that we saw in previous lecture, probability of A given B is equal to the intersection probability divided by the probability of B. If you want to think of the probability of B given A, it's the intersection probability divided by P of A. Now, if you do a little algebra and you multiply on both sides of this equation with the denominator, so in the first equation, for example, with P of B, we get this multiplication rule that the intersection probability of A and B equals the conditional probability of A given B times the probability of B. You look at this math and you say, oh, this looks kind of abstract. Actually, I'm sure you have used it, perhaps without knowing it. We use this rule actually all the time. So let me try to convince you that this is actually rather intuitive. Please recall this spreadsheet on Swiss population data that we have. If you look at the size of the canton of Zurich and the population of Switzerland, you will notice that 17.6% of all Swiss residents live actually in the canton of Zurich. And also in that data set you will see 19.6% of all Zurich residents are under 20. They're between 0 and 19 years old. And here's a question for you. What proportion of Swiss residents live both in the canton of Zurich and are under 20 years old? So look at the numbers. If I tell you 17.6% live in Zurich and from those people 19.6% are young, oh, what would you do? You would say, yeah, 0.176 times 0.196, that's now the fraction of people that have both. They are both young and live in the canton of Zurich. You do this and you get 3.45%. We have done this, I'm sure, in our lives a lot. If I give you half a cake and of that cake I cut it in 5 pieces, and then I give you a piece, how much of the total cake did you get? Oh, we started out with half. I gave you 1/5, 20% of that. You would say 0.2 times 0.5 is 0.1. I just gave you 10% of the cake. So we multiply these probabilities all the time, just as in this example or in the cake example. But now let's take a look at just this everyday calculation in the context of conditional probabilities. If we take these proportions as our definition of probability, the empirical probability concept number 2 from what we saw in the previous module, then we would say the probability that someone is from Zurich is 0.176. The probability of someone being young in the canton of Zurich, the probability of 0 to 19 years given the person is from Zurich, is 0.196. And now, if we use the multiplication rule, the probability of Zurich and 0 to 19 years old is then the probability of Zurich times the conditional probability 0 to 19 years given Zurich, blah blah blah, you do the math, 3.45%, exactly of what you did with your gut feeling before. So this abstract looking multiplication rule in conditional probabilities is actually an everyday concept, a proportion of a proportion, and then we multiply. Let me remind you once more of the concept of independence. Independence meant the occurrence of one event does not affect the chances of another event occurring. That was the probability of A is equal to the probability of A given B. If that's not the case, if they're unequal, we say dependence. Now, what happens if we take our multiplication rule and now assume that A and B are independent? In that case, the conditional probability of A given B is just the original probability of A. Now replace the conditional probability in that general multiplication rule and you get a specialized multiplication rule. And that's the multiplication rule I showed you in the previous module when we talked about independent events. The probability of A intersected B is equal P of A times P of B. Look, that looks much easier than the general multiplication rule. That's why people like this independent events assumption and this rule. Let's look at an example where we can easily use this. Let's say you play a dice game now with 3 dice. What's the probability of 3 ones? A 1 on the first roll, on the second roll, and on the last die. So, you want the probability of a 1 and a 1 and a 1. Rolling 3 dice, they are independent. I'm allowed to multiply the probability. 1 6 times 1 6 times 1 6 is 1 in 216. And there's nothing special about the 1 1 1. I can ask you what's the probability of first a 1, then a 3, then a 5. Same math. So you see, rather large, complex events like 3 numbers in a row, you can do this for 20 numbers in a row, for 200 numbers in a row, suddenly gets very, very easy under the assumption of independence. We can just multiply the probabilities. As simple as this is, we have to be careful in real-world applications. There often we have to ask ourselves, is that assumption reasonable? Can we really assume independence? If yes, great for you. We can use the independence multiplication rule. If, however, the answer is no, you are not allowed to use this rule. You may get into real trouble. And later on in this course, I will show you some devastating applications where people assumed independence and terrible real-world things happened. Here now, I want to give you a very simple example. Let's say you have a machine in an assembly line and that machine carries a heavy load and as a result, it breaks down on average in 1 out of 10 days. On 9 out of 10 days, it can handle the workload and it works fine. So if we use this historical data now and the equilibrium concept number 2, empirical definition, we can now say the probability of a good day is of working is 0.9, of a breakdown is 0.1. And here's now the question. What is the probability that this machine works 2 days in a row? So, if I don't know anything, I would have to say use the general multiplication rule. The probability of working well on the first day and working well on the second day is probability of working well on the first day times the conditional probability working well on the second day given it worked well on the first day. One probability I know, P of working well on the first day is 0.9. That's for my data. But what's the conditional probability? Now I'm in trouble. So now I would love to assume independence. If I have independence, then I can use the simpler rule for independent events at the bottom of the slide. 0.9 times 0.9, 0.9 squared is 0.81. But if I cannot assume independence, then I need more data. Now what is it? If you ask engineers like to talk about the so-called bathtub curve. A new machine often has breakdowns because it isn't perfectly calibrated, so the probability is maybe a little elevated, and a machine working well for a day or 2 or 3 indicates that the machine is calibrated and the probability changes. It reaches a low, it remains constant for a while, and eventually, due to wear and tear, it goes up. In the middle range, independence is an okay assumption, but at the front end and at the bad end, it isn't. So here we already see how a very trivial application of multiplying probabilities can result in rather tricky issues. Do we have independence or do we not have independence? And that's crucial for our calculations. And as I said, we will see more cool examples in lectures to come. Let me wrap up this lecture we have seen the general multiplication rule for conditional probabilities. Under the special case of independence, this multiplication rule greatly simplifies, but be careful assuming independence. Thanks for your attention. Please come back for more fun with probabilities. Thank you.